Euler's method makes this idea of following the arrows in a direction field to find an approximate solution to a curve more precise. In fact, it works out exactly what the algebra involved is. So suppose we have this initial value problem, y prime equals y minus x, where y of 2 equals 0. And we're looking for the solution shown in green here, which is the solution to the differential equation passing through the initial point 2, 0. So we decide how big the arrows are that we're going to follow, and we'd like to get an approximation to this green curve between 2 and 4, say. So what we do is we decide on a size for the arrows by deciding how far each arrow is going to move to the right. So in this case we're going to move from 2 to 4 with arrows where the x value changes by 0.2, and this is called the step size in Euler's method. And our first arrow brings us to a point where the x value is now 2.2 and the y value has also changed, and this arrow stays pretty close to the curve because it's a reasonably small arrow. The y value has changed, and we can figure out what that change in the y value is because we know the slope of this arrow from our differential equation. And then we can start at the end point of that arrow and draw another arrow where the x values move to the right by 0.2 units, and once again we know the slope of this arrow, so we can figure out what this new point is at the end of that arrow. And we can then follow the arrow in the direction field which starts at that new point until we get to a point where the x value has increased by 0.2. We can figure out the new y value and so on. And we can keep doing this until we get over to the point where x equals 4, and these line segments give us an approximation to the actual solution to the curve, which is shown in green here. So these red line segments give us an approximate solution or a numerical solution, and you can see that as you get further away from your initial point, these deviate a little more from the actual solution.